All right, welcome. We're just about a minute or so before start. We have 5 speakers in this session. We have timekeepers up here, 10 minutes plus 5 of questions. They have signs to hold up to inform new speakers, in particular Brendon Bradley, Mark Boland, Leone Pihama, Jillian Dabi, and Simon Keller. They're sharp-edged. If they're flung at you, your head will come off. Consider yourselves warned. Bit of housekeeping. There's a mic on here, so we want to record everything for posterity. So if you and posterity aren't on speaking terms, you're still required to pick it up because they'll get angry with me in the back. What else? And with questions, just give it a half-second wait. There'll be somebody with a mic from the back, and then you'll all be recorded for posterity. So if you have a silly question, what you do is you get up, you go, "My name is Jason Tilianakis." Sorry, Jason. And you can ask your question. So without further ado, I run the fastest Marsden panel, as Jill can tell you. So we'll keep this on time and on schedule, plus Brendon has to get home. His wife's been stranded with a new child there, and probably the emails will start getting nasty pretty soon. So forecasting the unpredictable, improving scientific understanding of earthquakes, and advancing seismic resilience, our new fellow, Brendon Bradley.
Thanks, Jeff. Just like this, huh? Okay, that sounds good. Okay, I guess the hardest thing for new fellows today is designing these 10-minute talks and trying to find the right balance of condensing their, shall we say, life's technical work down into a short period of time. But hopefully I can serve as a useful example of how to do that in the context of earthquake engineering, which as New Zealanders you're all experts in as much as me to some extent now anyway. When I first started working in this research field in the early 2000s in classic trans-Tasman rivalry fashion, our Australian colleagues used to comment that since 1931 there'd been more deaths from earthquakes in Australia than they had in New Zealand. Of course, the 1931 Napier earthquake being killing just on 200 people, and no deaths in New Zealand since that time, compared with the 1985 Newcastle earthquake that killed about 12 people. So they held that over us, if you can call that something to be proud of, for almost 100 years, about 80 years, and until, of course, the Canterbury earthquakes occurred in 2009. And I guess in some way, it's been very fortunate from my own perspective that many of the colleagues that I was initially mentored from in the field had spent 30, 40 years dedicating their life to earthquake resilience and disaster resilience, but never really had any event that would actually convince the public that what they were doing was worthwhile. So the earthquakes, like many natural disasters, are really an observation-driven science, and so the Canterbury earthquakes, just a few images that you can see highlighted on the slides here, really started to change the way we think about these problems in New Zealand, and I'm sure you all have your own recollection of something about those earthquakes that changed the way you think about things, whether that was a new scientific observation, whether that was the role of society working together, or many other good and bad things. So of course disasters impact a region in slightly different ways, and there were certain aspects of the Canterbury earthquakes which were completely foreseeable, others that were slightly less foreseeable, and then other certain phenomena that are problematic that just weren't observed in Christchurch at all because those conditions didn't exist. And so little over 6 years from the start of the Canterbury earthquake sequence, of course, we had the 2016 Kaikoura earthquake. Its location occurring in generally a rural area in New Zealand meant that many of the urban issues in Canterbury, like liquefaction of residential areas, damage to the central business district, they weren't present, of course, in the case of Kaikoura, but we instead had significant challenges to distributed infrastructure like highways, and several examples that you can see there. Many of you will remember, of course, that State Highway 1 was closed for about 11 months, which when you talk to colleagues internationally, that idea that State Highway 1, not 10, not 20, was closed for a year seems relatively unthinkable. Of course, one of the challenges that the 2016 Kaikoura earthquakes highlighted was actually that our capital city, Wellington, where we are here today, is much more vulnerable than we probably thought. We had a magnitude 7.8 earthquake about 60 kilometres from Wellington, and it already caused quite a lot of damage, and it's not the magnitude 7.8 underneath Wellington that a lot of people were thinking about. So it highlighted that the next event is not always the event that you think, and sometimes that can be for both good and bad reasons. Of course, never waste the opportunity of a good disaster, and so us earthquake engineers used our time in the limelight to make a pitch to government in late 2014 for a Centre of Research Excellence on earthquake resilience, aptly named QuakeCore, which has now been running for a little over 7 years. I presently hold the position of director within that core, and so it's been a really interesting journey to go from a sort of disciplinary researcher to move into the interdisciplinary space and see some of the interactions that happen when you bring lawyers and social scientists and geologists and civil engineers together and try and tackle some of these wicked problems that that really ultimately are the things that lead our research to be impactful. And so just as a comment on the 4 images that you can see here, some of the types of research there on the left-hand side is developing building technologies that actually go through large earthquakes without requiring any repair. The second is how do we substantially increase the densification of our residential buildings in New Zealand, so we don't just think of residential as single-storey or 2-storey dwellings, but actually multi-storey structures. At the same time, we know those multi-storey structures are the ones that traditionally do suffer more damage in earthquakes, so how do we put those things towards each other where places like Wellington want to significantly increase the densification of its housing. Obviously from the Kaikoura earthquakes and also cyclones earlier this year, we know that our transportation infrastructure is particularly vulnerable. New Zealand has a lot of challenges in that regard just because of how geographically sparse we are. I think the statistic of the number of highway kilometres per capita is the highest in the OECD, so that means we are faced with some significant challenges. But there is some light at the end of the tunnel, and that the fourth illustration that I have there is how we're trying to make use of disruptive technologies for seismic resilience. So if we can accelerate the adoption of certain technologies that are on the horizon, we may be able to get order of magnitude improvements in our resilience, possibly a decade earlier than we might otherwise be able to if we just let them happen in a sort of conventional adoption pathway. My own research personally is primarily in the area of modelling earthquake-induced ground motions. What I mean by that is sort of what's shown here in the animation, where for the 2016 Kaikoura earthquake, we model the earthquake rupture as it proceeds over the faults with time, and then how the ground motion or the seismic waves ripple throughout the Earth's crust, and they change in amplitude and frequency and duration as they traverse the Southern Alps and the Marlborough Fault Zone. And here's just an example of footage in the Wellington building and how that simulated ground shaking progressed over the Wellington region as well. So really what we're trying to do here is move in a weather forecasting analogy from the idea that tomorrow's weather is the average of what we saw the last 100 years tomorrow on the 28th of April, across towards where we make use of meteorological forecasts and we use our physics of the atmosphere to try and predict based on today what we see tomorrow. So we're undergoing that same transition for earth sciences. Of course, our problem is slightly challenged by the fact that the atmosphere is above us and earthquakes and the ground shaking they produce are below us, and then as a result of that it's much harder to obtain direct observations, and they're much more expensive to obtain as well. One of the other really interesting projects and outcomes that I wanted to mention briefly is depicted in these slides, which is an update of the New Zealand National Seismic Hazard Model. These two images are essentially the same. Hopefully you can appreciate that, for example, on the right-hand figure, the warmer colours indicate higher seismic hazards in the location where all our major faults are, like the Alpine Fault, for example, and cooler colours representing lower seismic hazards. They're really where a lot of our research has its impact in the way that we design buildings to be more earthquake resilient. And so this was a project that was completed in September last year. It had a team of over 50 scientists from New Zealand and internationally. A few of their logos are mentioned down the bottom, and represented a 10-year update on the prior national model that was available, and a 20-year update in terms of the last model that was scientifically used in the building code. So the dust has settled on the science from this release in September last year, and we're still yet over the course of this year to see the ripple effects of how this gets actually implemented in practice. So unfortunately, many of our buildings that are already shaky in terms of earthquake resilience are going to get a lot worse ratings on the basis of this new scientific information. So challenges ahead in terms of how we try and balance cost with risk at the same time as well. So thank you very much for your time, and look forward to any questions if there are some.
Questions for Brendon?
Thanks. So what are some of those new technologies that you think could bring us to a more resilient point 10 years earlier?
Yeah, so one of them, the easy one to convey would be around distributed energy generation. So we spend a huge amount of money on centralized electricity generation and distribution. So the annual maintenance costs for the Transpower national grid and the ongoing upgrades that are required to connect large centralized assets. And then I think we saw a really nice example of that in Cyclone Gabrielle, with the benefit of satellite-based Wi-Fi rather than centralized fiber optic cables. And so the same is true for energy generation. If households have their own solar panels, for example, then you're less reliant on one individual power station that happens to have a fault. And in that regard, even small amounts of energy generated can lead to significantly better outcomes than, so you don't need 100% of what you usually used. If you have 10% of your usual energy needs, you can still do relatively well. So things like that we see are one thing, and then the potential transition to partial or full vehicle autonomy is another one that will change the way we use roads and other infrastructure as well. Thanks for the question.
How is your organisation getting on with persuading local councils to do what the geological mapping says they ought to do? I'm thinking of lots of red stickered places in Christchurch, which were exactly where the geological mapping had said years in advance that liquefaction was likely to happen, and it did.
Yeah, I guess it's easy to take examples of things that happen and say we were right. There are many counterexamples where faults are present that don't rupture in hundreds of years. So I think that's the crux of the issue, that us engineers have a saying we like, that the number of faults in a region is proportional to the number of geologists looking for them. So they're basically everywhere, but actually we have to decide where to spend our resources wisely. And sometimes it's easy with hindsight to identify it could have been done better. I think the biggest issue we have at the moment is just we primarily construct facilities both for seismic resilience, but frankly for all other aspects of life, just to minimize initial costs, right? We very rarely think about life cycle costs for anything, and so that simple mindset of change is probably likely to give the biggest benefit going forward. Thanks for the question.
Any further questions? Well, I'll ask one then. And then we'll wait till 2:15 because people are moving rooms, and I'll make sure we get the timing right. I'll even let myself get recorded. So then if I look around Wellington and all I see is one of two kinds of buildings, new and or being retrofitted, so buildings with a crane, and buildings like, say, the Astron building, extremely large building, which we can class, like the education building, as buildings without people in them. So in that light, is what do you think, when you look at sort of 20, 30, 40% reductions in people working in these large office buildings, which are the biggest chunk of things that will take a hit with changes in fault status and risk level, versus, is this the perhaps only silver lining of COVID and working from home, that we may not have the rush on commercial property?
Yeah, I think that's a good point. And obviously we're seeing that internationally, places like San Francisco Bay Area, where they have 20% occupancy of their downtown office buildings. It remains to be seen. Of course, one thing that does seem likely to happen is that where office spaces has a change of use, it's more likely to be changed to residential high density. And so one of the things that happened in the Canterbury earthquakes, which was, I would say, kind of unforeseen, is that although we had damage to about 15,000 structures affected by liquefaction, actually the number of people that needed emergency housing was close to zero. People preferred to stay in their own home even if it was heavily damaged, whereas that's not the case for large multi-storey buildings where they simply cannot be occupied by law. And so I think one challenge in that regard will be, as we move to these many-storey residential buildings, 10 plus stories, is they need to be substantially more resilient than they currently are. Whereas evacuating an office building and not going into it for 2 months is not good, but maybe plausible. But identifying that 10, 20,000 people need to find new housing for 2 months is a completely different question.
All right. Any last questions? Jenny?
I found it really interesting in the Kaikoura earthquake, and I'm sorry if I've got the building wrong, but I think it was the IRD, the direction of the seismic waves came from an unexpected direction. So buildings that were built supposedly to code were not to code because it came from another direction. Can you comment on that? Because I assume that's part of your working out.
Yeah, that can be the case in some instances, although usually that's a bit of a misnomer for other reasons. So the building can respond preferentially in one direction, not because the earthquake was stronger in that direction, but because the building was a lot weaker in that direction. So typically, if you have situations where like one side of a building is a lot of concrete walls and the other side is a lot of glass space with flimsy frames, then the building twists substantially and you can get much more damage in some places than others. So it's more likely that reason rather than something to do with the ground shaking itself. Thanks for the question.
All right. Thank you, Brendon.